Now, with part B, it was rectangles of height 1. So in part B, we said, okay, well, let's do rectangles with a height of 1.
Oh, you see the height?
Yeah, they gave you the height. If you
I
read
did not read that.
B, rectangles of height 1. So when we go to do this, is the graph going to change? No, because we're still working with the same curves. Is our distance B from top to bottom going to change? No. Is our 2D cross-section going to change? Yeah, because now we're not doing squares, we're doing rectangles of height 1. So I'm going to cross this out, and I'm going to do a rectangle with a height of 1. The base of the bottom of the rectangle is still B, but now the height is 1. So instead of area equals B squared, now my area is going to be area equals base times height. My base is that thing, negative x squared plus x plus 2, and my height is 1. So area equals this negative x squared plus x plus 2. And once I've got that, I dump it in here for my integral, and that's going to be my volume. So instead of having this thing here like for my squares, now my integral for the rectangular cross sections of height 1 is just going to be negative x squared plus x plus 2. So for the rectangles, if we're going to do cross-sectional rectangles, they either have to tell you the height is, explicitly, the height is 1, the height is 7, the height is whatever. Or they got to tell you the height as like a relationship to the base. The height is twice the base. And then the height would be whatever 2 times that is. Or something like that. So they got to give you something explicit about the height, either what it is as a constant or what it is in terms of base. Because otherwise you have no way of knowing what the height is for the rectangle if they do rectangular cross-section. So that's 71. Part A was the squares. We looked at that first, and then part B with these rectangles. And they tell you the rectangular height is 1. All this stuff at the beginning is the same with the graph and the B. The only thing that changes is the shape of the cross sections and therefore the area formula. Anything else with 71? Anything else with the homework? Okay. So the washers and discs on the homework went okay?
Dan Nelson, please take room 322 for coverage. Dan Nelson, please take room 322 for coverage.
They didn't tell us to get to our classes. Okay. Yay. All right, dice. 1, 1, 3, 4, 6. So I'm collecting rows 2 and 5. So Michaela's row and Renee's row. And we've reached the end of a whole 2 pages of my gradebook homeworks. So from the beginning of the year till now, we've filled up all of these columns.
That's it.
Yeah, that's it. I'm surprised.
Me too.
It feels like it's been more homework than that.
Yeah. You never ask yes or no.
We don't have time for that sort of stuff anymore. All right, get out the packet from yesterday. You get a default yes if you hand in your homework that it's I collect you, or if I don't collect you. Yeah, this is. If I didn't roll, I didn't collect row 3, right? So row 3 got yeses. If that's okay.
No, that's fine.
If your conscience afflicts you and you say no, I don't deserve a yes. Some of you are like, what is a conscience?
We're not taking that.
If I don't have a conscience, is that like when I'm not conscious? Like, all right. An extra packet.
I never knew what the word was.
Okay.
I would say it and
Actually, I have an extra packet, but it's got other people's name on it because like they weren't here to collect it. What's that?
I mean, I was a child. I don't
Yeah.
All right. So tonight is going to be to finish this packet. So we got to decide what stuff worth doing together and what stuff worth letting you try. So
We will
examples 2 and 3 both involve circular or semicircular cross sections. Which one?
To win 3. Hang on. Do the second one.
three,
Do the
do
second one.
three.
Do the second one.
Do the second one.
Well, example 3. The second one.
Yeah, do the one with sine of pi
This
x.
one.
Sine of pi x. All right.
No.
When you go to do example 2, just be careful that we're perpendicular to the y-axis on that problem. All right, example 3. So our region is going to be in the first quadrant. So when you see, oh, they're specifying the quadrant, keep that in mind. And it's going to be bounded by the graphs of sine of pi x. So we got a graph sine of pi x. Thank you. So I guess since we're in the first quadrant, I can put the y-axis way over here. So sine of pi x. What's sine of 0?
0.
Hey, that's a good start. And then sine of pi over 2, 1. When will I get an angle of pi over 2 in here when x is 1/2? So we can just count by halves and forget the pi because pi is built into the function. So we got up to a height of 1. And then what's sine of pi? 0. And then sine of 3 pi over 2, or 3/2 pi, is like that. And then sine of 2 pi is 0 again. So that's your sine curve. Then, and we're only in the first quadrant. And since we're only in the first quadrant, even what I have is too much, right? What can I get rid of? Everything after x equals 1. I can just do up and down. That's my first quadrant. When I went down here, what quadrant was I in? 4. So, not quadrants 1 and 4, just first quadrant. Boom. That's all you get from sine x. Then, y equals x minus x squared. X minus x squared is 0 and 1. And that's going to go which direction? Down, right? Because it's a negative x squared. Wait a minute. It's going to go up. So, oh, no. So who's higher? The sine curve or the x minus x squared curve? Well, let's plug in 1/2, right? Sine reaches its maximum at 1/2. I don't know who's higher. So what's 1/2 minus 1/2 squared? 1/2 minus 1/2 squared is 1/2 minus a fourth. So it's a fourth. So the sine curve starts at 0. The x minus x squared curve starts at 0, ends at 1, 0. So they intersect there, and then in between only gets a quarter as high as the sine curve. So the sine curve gets all the way up to 1. The parabola only gets up to a quarter. So we have sine on top, and the other guy on the bottom. I'm not going to write it in there because that's going to get too cluttered. So the parabola is opening down. Yeah. So that's our graph. Then we're going to have cross sections perpendicular to which axis? X-axis. So I always draw a little horizontal. By horizontal, I mean rectangle. Because those are in any way relevant to each other. Yeah, I meant a rectangle when I said horizontal. Sorry. So I draw a little rectangle perpendicular to the x-axis there. And that, what's the distance of this thing? Yeah. What do we give this guy? B. So that's B, and B equals sine of pi x minus x minus x squared. Next, we look at the cross sections. So we know the cross sections are perpendicular to the x-axis. What are they? What are those cross sections? What shape? That was annoying. All right, thank you. So circular cross sections. So our cross sections look like this.
Full circle?
Full circles, yes. You gotta if it's a semicircle, they will explicitly say a semicircle. If they want circular cross sections, then that's a full circle.
So you're telling me this is the graph and it's just going like.
Nope. So this isn't sitting like here. Keep reading. So the cross sections are circular and they're perpendicular to the x-axis with diameters lying in the region. So your diameter is B. So the diameter of our cross section is lying in the plane. Half of the circle comes out of the page at you, and half of the circle goes into the page, and away from you is like behind the paper. Answer.
So, finding the volume of the circle, right? Or not the circle, but the sphere
Yeah.
created by the circle.
Yeah.
So we have to double it? Or no, we just use the circle area.
We'll just do your area formulas for a circle. So I say, what's our area formula for a circle? Pi r squared. What's the radius? 1/2 b. So pi times 1/2 b squared. Clean that up, and that's what's 1/2 squared? 4. So 1/2. 1/4. You get 1/4 pi b squared. And then what do I still need to do with this before I go to the integral? Put it in terms of x. So our area formula is going to be ugly. 1/4 pi, that thing, sine of pi x plus x squared minus x, all squared. And then this is probably a good time to use your graphing calculator to evaluate the integral. So, to that end, let's remind ourselves, how do we make the calculator work for us? Yes, ma'am.
So when you memorize like area formulas,
Mhm.
would it be easier to memorize like the circle and the semicircle being in terms of 1.5 or 1.8
Maybe. I don't want to confuse you with your actual formula for a circle, though.
but like we always use these, so it's just easier to memorize it in terms of rather than
If that's helpful for you, then do that. That's not going to be something
so
that I
it's
like.
gonna stay the same, like all
It's gonna, yeah. So like, the diameter for a semicircle or a full circle is always going to be the diameter lying on the plane. So this B here will always be the diameter of your circle or semicircle when you have that. So when we go ahead and do this on a graphing calculator, oh, I'm seeing a problem with this. I don't really want to erase that. But, all right. So our integral for the volume is going to be integral is from 0 to 1, right? So integral from 0 to 1 of this whole area thing, dx. So instead of rewrite the whole area equation that we made, I'll just put an arrow dumping it into the integral. So how do you do this now on your graphing calculator? First, you get out your graphing calculator. Then you turn on your graphing calculator. Then you go to y equals. And then you type in the entire integrand, even including the 1/4 pi. So like normally, if you were going to do this integral by hand, you would pull out the 1/4 pi out front so that it doesn't clutter up all your integration steps. But since you're doing this integral in the calculator, you got to include the 1/4 pi in your calculator stuff. So I'm going to say, all right, let's type in pi over 4. And then that's going to multiply the entire sine of pi x plus x squared minus x all squared. So I'll just type in what I see. So sine of pi x, close the parentheses around pi x so that you don't put everything inside the sine function. And then plus x squared minus x, close the parentheses for the entire thing after 1/4 pi. And then also make sure your calculator is in what mode? Radians, because if you do this in degrees, you might have beautiful work and you did everything correctly, and then your calculator will lie to you because you lied to it. So make sure your calculator's in radians. So once you do that, you go ahead and hit the graph. And you're going to integrate just from 0 to 1. So hit second, trace. So once you've got your graph, now does anybody not see the graph? Or is anybody getting an error? Because we've got to know how to deal with those problems. So second graph, to see the graph, zoom, and then Z standard will reset your viewing window. Oh, that's kind of cool. And then to do the integral, second trace, integration option 7, and then you're going from 0 to 1. So type in 0, hit enter, type in 1, hit enter, and your calculator thinks about it. And then down at the bottom of the screen, it shows you what that is. And I can't see that because of all the clutter up here on the board. It is, now my cursor is still in the way, 0.369. Well, I need to be able to see. So the volume is 0.369.
So that was not hand solvable.
It's probably hand solvable, but you're going to end up with a sine squared item. And in order to integrate that, I believe you would have to use one of the power reducing trig identities.
So I got 0.12.
Interesting. Here you go. So what did you type in? 1/4 pi sine of pi x plus that x squared minus x. Oh, I see what you did. You have an extra set of parentheses around just the x squared minus x. You don't need that. Ooh, I might have forgotten to square it. Yeah, so I think you're right. Thank you, Michaela. So Noel, you made a different mistake than I did. Noel had an extra set of parentheses just around the x squared minus x, and then he squared that. I just forgot to square all of it. So, oopsies. Graph that. That's what it looks like. If you want to see what it looks like better, you can zoom in and get a better picture of it. That's kind of cool.
Yeah, that's what I got.
All right. And then second trace, still doing the integral, still going from 0 to 1, and 0.216. All right. Is that what we got?
Yeah.
Hooray! So make sure you type stuff in correctly. It's not just good enough to make sure you're in radians. You got to make sure that you, now if this is like on a free response question on the exam, and you set it up on paper correctly, and then you jack up something in your calculator, I would bet you get all the points except 1 for the answer. So if this is like a 4-point thing, you'll get 3 points for all this work, and then you just won't get the 4th point for having the correct answer, as long as all your paperwork of like the picture and the cross-section and the area equation and the volume integral, if all that stuff is beautiful and all you did was mess up the calculator, you'll get all the points except 1.
So are all the other problems that we like do by hand still solvable on the math calculator?
Yes.
So technically I don't have to do work, I just have to subtract like things.
So you can always do this on the calculator. I'm saying let's do this one in particular on the calculator because we don't have the tools from what we've learned to do this one by hand. And even if we did have the tools, that one's especially heinous to do by hand.
So if I
Do
did
it by hand. No.
ones on calculator and I was just like, oh yeah, I did it on the graphing calculator.
That's fine. Unless, like, I specifically in the directions say I want an exact answer, no rounding off a decimal. Like that answer that we got, this is not exact. This is probably a forever decimal, and this is rounded off because it's got to round off somewhere. So if we wanted an exact answer, you would have to do it out by hand. And that's, you give a fraction with a radical or pi in the fraction. It involves that. Like here, obviously, you're going to have a pi in your answer if you do it exact. because there's a pi built into your sine function.
And on the outside.
Divide by pi. It's not pi on.
Mm,
It's multiply pi in. Divide your-
but you've already rounded off. Like the decimal that's there is already rounded off.
Oh.
So dividing by pi, you're dividing a rounded off thing. Moving along. So example 4 is
I don't think the sine of pi does it, because sine of pi
a little trickier. So, example 5b. What are your cross-section shapes? It says isosceles right triangles
Yeah.
with the base as a leg.
That's the better one.
Yeah, that's the better situation.
Can we still do that again?
Let's do, no, I want us to do example 4 together.
Oh, that's fine.
Because here we're having an isosceles right triangle with a hypotenuse in the base. We see the word circle, you might think, oh, cool, circular cross sections. No, that's the base. So, example 4, let's try to set this one up. A solid has a circular base of radius 2. What's the equation for a circle of radius 2? Not the area equation, like the equation that makes a circle.
X squared, y squared, and plus y squared.
All right, x squared plus y squared equals 4. So the base is a circle. We need to come up with the base. And the base is the area in the plane. And then we want to be able to like turn that into equations like a function. And we're cross-section is perpendicular to the x-axis. So we want to be doing things in terms of x. So let's get y by itself. What's the circle equation as a function of y, or a function of x? Root 4 minus x squared. And because it's a full circle, what do we need to include? Plus or minus. So we have the top half and the bottom half. So that's our equations just for the base. And if we draw that, we have a circle of radius 2. So it's going out to positive 2 and out to negative 2 on the right and left, and up to positive 2 on the top and down to negative 2 on the bottom. So that's the reason that we're dealing with. So when they say, hey, your circular, your base, the base of the solid is what you see in the graph. So in the previous problem, the base was that region between the sine curve and the parabola. Now, your base is a circle. You got to know the area, not the area equation. You got to know the circle equation, and you got to be able to then turn that into a function notation. So if I draw my rectangles on here are going to be perpendicular to the x-axis. My representative rectangle. And then my 2D shape, my 2D cross sections are what shape? Isosceles right triangle. Now, where's the hypotenuse? Or what's the base? B. So this base is this time the hypotenuse. So the two equal sides are these guys, and that's the right angle. So this is where knowing your area formula for this kind of isosceles right triangle, where you know the hypotenuse rather than one of the legs, is helpful. What was it? I think it was 1/4 b squared. That's my memory. The other one is root 3/4 b squared. So if it's an equilateral triangle, it's root 3/4 b squared. If it's isosceles right triangle and the hypotenuse is your base, this guy. And if it's an isosceles right triangle and the base of the triangle is the same as one of your legs, then it's 1/2 b squared. So you have 3 different area formulas for triangles, depending on what kind of triangle it is and how it's oriented. But they all have b squared. So it's either 1/2, 1/4, or root 3/4. Or square root of 3 over 4. Yeah, so not root 3/4. Sorry, it was root 3 over 4. I lied in the notes. So yeah, in the notes I had 3/4. I forgot to square it over 3. So watch yesterday's video. And oops. So now we got to come up with what's b. So we come back over here and say, all right, cool. What's the distance b here from the top to the bottom of this curve, of the circle? Yeah. So positive this minus negative that, which will in the end be 2 of that. So the positive radical minus the negative radical, the radicals themselves are the same, so then you have 2 of that radical. So 2 square root of 4 minus x squared. That's the distance from top to bottom. That's going to come over here. And we'll have 1/4 times 2 times the square root all squared. And then you just got to be careful with how you square stuff. What do we end up with? 4 times 4 minus x squared. And what happens with the 4? 1. Cancels out with a 1/4. So we're just left with 4 minus x squared. And now, oh wow, it's going to be so easy. So, because now this is going to be super easy to integrate. You just take this thing, put it in an integral, and you're going from -2 to 2. You could make it even easier and say, this is symmetrical. Let's just go from 0 to 2 and double that integral. So we'll have our volume is the integral from -2 to 2 of that area equation, 4 minus x squared dx. And you can simplify it further. Double the integral from 0 to 2, still a 4 minus x squared dx. So once you got the area, if it's a nice area formula like this, it's like, hey, this worked out really nice actually. Again, the heavy lifting is on the front end, coming up with b, coming up with our area equation, and so on. So I'll leave it for you guys to finish this because we're out of time. And your job tonight is to finish the packet. You guys still have examples 2 on page 2
That's done.
and example 5 on page 3.